All right, so we're going to start. We're going to talk about Cryptography 101. A little bit about myself. So my full-time job, I'm an ASP.NET developer for an e-commerce website in the US. And I did give my Twitter, my email, and my blog information. So I am going to provide the slides and the code. So I have a link at the very end that has the slides, and I have two versions of the code. I have it in .NET 5, and I have it in .NET 4.8 in the full framework. There's not a lot of differences between the two. I'll call out a few things during the talk, but both of those will be available to you. And the point of the talk isn't specifically about .NET or C#. The concepts apply virtually regardless of what language and framework you have. They have good access to cryptography libraries, but I just happen to be a .NET developer and use C#, so that's what I'm going to show it in. So we'll start right in. So cryptography is the science of keeping messages secure. So why do you have cryptography? If you asked people on the street and said, what is cryptography, or and asked them how they would react, most of them are going to talk about confidentiality. So they may not have even heard of cryptography, but if they've heard of encryption, they think of confidentiality first, which is you want to protect the data from being read. You have something you don't want people to see, and that's certainly important. But we're also going to talk about integrity. We want to verify that data was not modified. We also use it for authentication. So we're going to use it to identify and validate a user. And we're going to talk about it for non-repudiation, which just means a sender cannot deny later that they sent a message. So that gets into digital signatures. Within .NET, it's system.security.cryptography is the namespace where the classes are going to be found. There's a lot of considerations when you look at cryptography. So first of all, again, what is your goal? I see people misusing cryptography because they're not clear on what they're trying to accomplish from the goals we talked about before. So I'm going to map techniques we talk about during the talk back to which goals they apply to. Consider how much is your data worth? How long does it need to be secured? A couple days, decades? Think about what your primary threats are. So like I said, I'm an e-commerce developer. I have web servers that sit on the open internet. Obviously, we have security mechanisms in place, firewalls, web application firewalls, all that sort of stuff. But I still have to think about how would someone attack me? And so from my perspective, I obviously care about in transit. So we'll talk about HTTPS. I feel like my web servers are compromisable. So I treat them like on any given day, there could be a 0-day exploit and somebody could own my web servers. So these are the things I would worry about. They could access my config files. They could take a dump of memory, which would have any in-process things that I store in a string would be something they could see. They could modify my pages. They could reverse engineer my assemblies. So throughout the talk, we'll talk about layered defenses and other things, but it's very important that you think about how would somebody attack this, because a lot of the flaws we'll talk about during the talk, people just didn't think through how people would abuse it. So I also did a capture the flag this past year for the first time ever, and it was very interesting to see from an attacker's perspective. I've heard of all the attacks before and I knew what I should do to stop them, but coming at it from somebody who's attacking your site definitely changed my perspective and made me think about threats a lot differently than I had before. I'm sure you have to deal with company security policies, regulatory compliance. So because I have e-commerce, I take credit cards, I have to be compliant with PCI in the United States. I want layered defenses. And so the question is, how many are enough, right? If you think about security, the only truly secure computer is going to be shut off in a lead box in a corner, right? I can't do that. I still have to have an e-commerce site. So I need to understand the risk versus reward, and I have to decide on layered defenses, and we'll go through that throughout the talk. If you don't take anything else from the talk, please don't write your own cryptography. So I've actually run into people that have said, you know, I don't want to use a standard library that's been well tested, proven to be secure. I think if I wrote my own, people wouldn't know the algorithm and it would be secure. And there's just such a history of failure around this that please don't write your own. If you really want to be a cryptographer, get involved with an organization that is their focus, where you can be amongst others, code reviews. Even people that are very serious cryptographers make mistakes. And so please don't try to write your own. How the .NET algorithms are implemented. So I gave you a link there. I just want to point out that you'll see classes in .NET that have suffixes like managed. Those used to mean things in the .NET framework. So if it were managed, that means the algorithm was actually written in a managed language like C#. So IL eventually. CNG was cryptography next generation, which is in some of the newer Windows. Crypto service provider was in older Windows. The reason it mattered is if I were doing government work and I wanted to be FIPS compliant, it turned out the managed implementations in .NET never got FIPS certified. And so there's trade-offs about deployment as well, right? If I pick CNG and I want to run it on a system that doesn't support that yet, that's not going to work. So like I said, in the .NET world, those things mattered. In .NET Core, .NET 5, all of these classes with all the different suffixes just wrap operating system libraries. So all of them ultimately end up using the exact same thing. So I'll show you in the code. I've got the other ones commented out. I've just switched to using the default classes and not worry about any of the suffixes because I'm doing it in this case in .NET 5. The other warning, I gave you a link. It's true that .NET Core, .NET 5 are cross-platform, but not every cryptography class is available on every platform. So it would be unfortunate if you did all of your developments. I traditionally do Windows development. If I did it all on Windows and then found out when I went to deploy to Linux, for instance, that a given library or class is not available. So you can actually go to that link and it'll give you a breakdown by class, whether or not that is supported on a given platform. So just make sure you check that if you're doing cross-platform work before you get too far. So let's jump into some of the techniques. So the first thing we're going to talk about is hash functions. So this is one of the foundations for cryptography. It's what's called a one-way function. It's easy to compute in one direction. I put it's hard to reverse. People say impossible. Obviously, I don't love that word just because those things have been proven to be possible at times. You want the one-way function to be incredibly hard to reverse. That's a good cryptographic hash function. So if you see an example, I've just got some text on the left-hand side here. When you compute a hash, it creates this data fingerprint or hash value. It's a fixed length based on the hash function. So regardless of how big the left-hand side was, once I choose the specific hash algorithm, this will always be a certain size. And we're going to use this for both integrity and for authentication. So in .NET, the abstract base class is called hash algorithm. There's a lot of specific classes underneath that. So I listed them here. I did a strike through with ones that you don't want to use. So I talked earlier about using trusted libraries. I don't want to write these things myself, my own implementation. I personally want to use what's built into .NET. Just because if you take the flip side of that, just because it's in a framework doesn't mean that it's secure. So in other words, MD5 has been around forever. It's included in .NET because of backward legacy compatibility. It's something you never want to use today. So it's considered broken. So I just list it here and put the slash through it. Don't use it on anything new if it's for cryptography. And if you see it in something else, you want to actively move away from this. The same is true of SHA-1. So PCI dropped SHA-1 a few years ago, where you wouldn't be considered compliant if you were still using it. And you've seen a lot of vendors move away from it. It's still in a lot of use, but it's also considered broken at this point. SHA-2 family of algorithms. So I listed the specific ones here. SHA-256, this is just the number of bits of the result, 384 or 512. Those are all available. That's still considered at this point to be secure. There's actually a SHA-3 family. So there was a competition a few years ago. NIST decided that they wanted to have algorithms basically ready. So if suddenly on some day SHA-2 gets broken, they want something that could take its place. So they did a competition. They've chosen the winners for SHA-3. I don't list it here because it's not currently available in .NET. And so again, company policies for me and my personal philosophy, I'm going to use what's built in .NET. SHA-2 is still considered secure, so that's what I'm going to focus on for this. I might be able to find George's blog, right, where George might be a great guy. He took SHA-3 and decided to implement it himself and make it available. I'm not going to use that, right, for my production system. So that's why I'm just not listing any of those here. There's also what's called key hash algorithms, and we'll see why we need these. They are hash functions that also require a key. So you can see the name of those classes. And again, we'll talk about why you'd want to do that. So let's jump into some code. So I've got a simple page here that's going to hash. So I have a string that I want to compute the hash of. So here's where I'm going to create my class. So I'm going to use SHA-512. I want the most bits that I can get. So that's what I'm going to use throughout the talks today. You can see I've got the other suffix classes that I mentioned before. There is a managed and there's a crypto service provider. Again, in .NET 5, these will all actually go down and use my supplied operating system's implementation of SHA-512. I just wanted to show you that they are there, and I'm going to use the default. In order to compute the hash, we all deal with strings, right? I mean, I'm typically, all the things I'm doing, names, etc., are strings in .NET. The cryptographic libraries are all based on bytes. So I need to constantly convert between strings and bytes. So there's a number of ways. We're going to look first at taking the string and switching it into bytes. There's an encoding library in .NET. UTF-8 is a very popular, UTF-16. If I'm only doing this for my own usage, it really doesn't matter which one I pick. So I just happen to pick UTF-8. If you're working with a partner, however, and you're going to send this hash between you, you're going to want to make sure that you pick something consistent. So the first thing, again, I have a string. I'm going to get it into a byte array, and then I'm going to turn around and compute the hash of it. What I'll get back is a byte array. So if you look, I put in the comments here, SHA-512 is 512 bits, 8 bits per byte. It's going to be 64 bytes for the hash result. And then I want to be able to display this on the screen. So I'm going to show you what this would look like. I want to be able to display what it hashes to here on the screen. So I chose to display it as hex. I'm going to show you throughout the talk some variants and different ways that you might want to change it to from bytes to a string. But in this case, there's a bit converter class built into .NET. So I can just say convert that byte array into a string. It's going to put each byte in its hex representation. And then I chose to take out the dashes. So the end result looks something like this. The other one you'll see a lot, base 64. There's various reasons I'm going to use this, which you'll see as we go forward. So I just chose to do that as hex. But what I want to stress is back to the don't write your own. If you need hashing, SHA-512 is very well known. It's considered secure yet today. It's built into .NET, so it's been tested, open source. People can look at it. So I want to use the library, and you can look that taking out all my comments specifically, this is not a lot of code to accomplish what I want to get from hashing. So it's very easy. For a company, it'd be pretty common for me to write a wrapper and create our own company library that hides some of the implementation details. But even if I use this directly, this is really straightforward and easy to implement. So that is hashing. Where would be a practical place that you could use hashing? So if you've been to websites before, I'm sure you have, where the URL has maybe customer number equals 123, for instance. It'd be unfortunate if I could go to the 123, change it to 124, knowing that databases are typically sequential IDs, and then I could see another customer's data, right? I don't want people to be able to do that. So the idea with tamper-proof query strings is let's use hashing techniques and use it to protect the integrity of our query strings. So in this case, I'm going to use an HMAC, a keyed hash, and I'll show you why. So the concept is I have a query string I want to use on a page. I'll compute the hash of it. I'm going to put that hash on my URL. Then when it gets sent back to the server, the server can pull off the query string, rehash it, and then compare the hash it just got with the one that was sent and make sure they're the same. If not, somebody has modified this query string. So again, the goal is I just don't want people to be able to hack on the query string and see things. I don't care if they see the values that are up there. This isn't a confidentiality issue. It's an integrity issue. I want to make sure that they're not changing anything. So if I look at an example here, I have a hyperlink. If I click it, I can see up here on my URL, I've got A equals, I'm going to try to hide my thing here. Move this out of the way. So I've got A equals 1, B equals 2, C equals 3. Those are the query string parameters I'm going to try to protect. And what I want is I want someone to not come here and say A equals 2 and hit enter. So I'm going to give you some warnings throughout the talk. I want to give you this code, right? So it's important that this is something I can demo for you. I want to show you this while I'm doing this talk. I'd never do this in production, right? Never show my error messages like this specifically to an attacker. It's just going to give them an advantage because they know I'm using hashing. They know it doesn't match. It tells them more than what I want them to learn. But for the demo, I want you to be able to see what exceptions are occurring. So again, I protected the integrity. So if I were an attacker, I want to think about the threat model again. What would I do if I wanted to attack this? Well, I could come over here and hope to get lucky and change this C to a D, right? Still doesn't match. I could come up here and say, well, maybe I forgot. If I were to just delete that, what would happen? You can see the validation was not sent. So I had to think through some ways of how people would attack this and come up with countermeasures, right? So why did I use a key for this? Let's look at the code. If we look at the setup tamper proof. So here I've got my query string, the A equals 1, B equals 2, C equals 3. So one note is I need to use code now to create my hyperlinks, right? I can't just link in markup like I used to. I need to run some code to compute this hash. So as I said, I wrote a common function here just so others could use it. And it takes the data, what type of output I want, whether that's hex or base 64, whether I want to use a key or not, which is here, and then some other data we'll get to momentarily. This will look pretty familiar. If I'm going to use a key, if I'm not going to use a key, I'll just do what I did before. If I do want to use a key, I'm going to use the HMAC version of SHA-512. This requires a key. Again, I'm going to give you the warnings throughout the talk. I'm not going to store my key inside my code like this. Why? Because this is going to end up in version control. This is going to end up being built into my assemblies, so someone could reverse engineer them. So again, for a demo, I want to be able to give you this. We'll talk about key storage a bit later, but just be aware, not something I want to do. But for the demo purposes, I've got my specific key here. So because I use the key, I compute the hash, I do the output, and everything is what you would expect. So again, if I were an attacker, if I were looking at this and I saw what you're doing, I'm going to guess based on what I see up here that that's probably hashing because somehow it's figuring out that I'm tampering. If I took that size, I could figure out that that's 64 bytes worth and that it's probably a 512-bit hash. There aren't that many of them. So I could write code, and I gave you an example here. I'm not going to go through the entire thing, but I can write the same code you write, right? I can do computing of hash just like you do. I'll just compute the hash of what I want and everything will be okay. Well, we talked about layered defenses before. By storing this key, it's made it more difficult for an attacker. So an attacker can't just figure out everything I just said. They also have to be able to compromise my server and gain access to my key. So again, from a layered defense standpoint, like I said, I wouldn't store it here. Normally, I'm going to put that somewhere more secure, which will be another hurdle. If I were to take this off, you can do this later. I can actually take off using HMAC and just use, I can say, don't use a key. And then I would be able to go run my own computation and then just go replace it up here in the URL. I could put 2. I know the right hash if there wasn't a key involved, and I'd be able to tamper with your stuff again. So just a good example of layered defenses, thinking through how you might get attacked, and making sure that you have that extra layer of security. So that's a good practical use of hashing for integrity. Another practical use is for passwords. So Unix years ago first looked and they said, we need to store passwords for people, right? They looked at cryptography. We're going to talk about encryption later, but they happened to stumble on hashing. And they said hashing is great because it's not reversible. If we take your password, compute the hash of it, let's store the hashed password in our file in Unix. And therefore, we have faith it won't be reversed, will be super secure. And they wanted to use that for authentication. They got a little too excited about it, and they said, there's no reason the Etsy password file can't be readable by everybody who is signed into Unix, because we know even if you can read it, you can't reverse passwords. So why bother to hide it? If you think as an attacker would, they're not going to try to reverse your hash. If they're using a good hash algorithm, it's not going to be something they're going to be able to reverse. But what they didn't think about from an attack standpoint is people could pre-compute a list of words that might be the password. So I did research while I was in college years ago, and basically you'd take a dictionary. So you'd take the complete dictionary, you would hash every word in the dictionary, guessing what hash algorithm was used. Then all you need to do is compare your hashed value to what's in the password file, and you'd break. And back then people would get 60 or 80% of all passwords they would break because people made poor choices and were using dictionary words. So if I show you an example of how you could do that. So this is the hash password that I would have taken from the password file. This is what I'm trying to, I'm not trying to reverse it, but I'm trying to guess what it might be. So in .NET, I just created a dictionary of some words it might be. Attackers take this, online dictionaries. If they're serious, there's also lists of known passwords from breaches. So they'll actually do dictionary words and then these lists of passwords that have been in previous breaches, all of that stuff they'll throw into a dictionary like this. Then all I need to do to crack it is say, is this hash match anything that I hashed up above? So if I were to run that, you can see in this case that is actually secret. So I have not reversed the hash algorithm. I haven't cracked whatever technique was used for this. But what I did is I guessed what it would be and put it in there. So they realized their flaw and they decided to come back and add one more layer of defense. So they did what's called salted passwords. So here they said, rather than do the hash of everybody's password, let's take some random data that's unique to each user, and they called that salt. And they would, when you came in and typed your password, they would take your salt and they would hash it. They would store that then in the password file. So what that's done is it's made it, if I'm an attacker, I can't just pre-compute the entire dictionary, all the hash values, because now I need to pre-compute the dictionary with your salt and the words that are in the dictionary. So it just made it harder for an attacker. They can't easily pre-compute the entire dictionary like they did before. They need to do it for every unique user. So that was an improvement. It made it harder to attack the entire file. But if you think about it, it didn't do anything to increase the security of an individual password. So if I were on Unix already and I'm trying to break into other accounts, I would have taken the password file, I would have found the admin account, take their salt, and I would have pre-computed the dictionary and all the words for the admin user. Because if they made a bad choice and I get the admin, I have root now and I'll be able to get anything that I want. So it was an improvement, but it's still not perfect. So let's look what that code would look like in comparison. So here's the data. I generated some salt. We'll talk about that. So this would be specific to each user. So each user has a different value of salt. I just compute the hash the normal way. I can compute the hash by passing in the salt. So all that does, if I go look at that definition, it takes the password as it did before, right here, and it just concatenates on the salt. So if I do that, that's going to be better because now that hash will be specific to that user. It also protects that previously, if two users both had 1, 2, 3, 4, 5 as their password, they would have had identical hashes. Now that they each have a different salt, that won't be obvious anymore. They won't show the same hash. Talking about layered defenses again, I think it makes sense to do a server-side secret as well. So now an attacker, not only would they could look in the password file, they could see the salt used for you, but because I have this other piece of data that I also concatenated, now I've made it a little bit harder again, right? And again, I wouldn't store it here in the code, but as an example, now they also need to be able to get this before they can compute all the hashes. So it just makes sense from a layered defense. What do people actually do today for passwords? They use something more like PBKDF2, which is in .NET. If you've heard of bcrypt, scrypt, some of those algorithms. And the idea with these is they're hash algorithms that are meant to be intentionally slow. So in other words, I get to choose what's called a work factor. So I can choose how slow I want the hash function to return a value at. So this is easier to show you in the code. So here, I'm a Led Zeppelin fan. That's not really my password, but pretend that's my password. Pretend this is some salt. What I can do in .NET again, I'm going to use this. This is the secret. I want to choose a value for my current hardware. So take my website, right? If I want to use this technique for passwords on my website, I need to choose a value of this iteration count that makes this algorithm take a certain amount of time to compute your hash. So I may decide half a second or a second is reasonable. The trade-off is every time somebody comes back to log into my website, I'm adding an additional intentional second to their login time. So I'm penalizing normal users of the site who are trying to log in and do their business. The reason I'm doing that is now an attacker that wants to pre-compute a bunch of dictionary words, they can't do it fast. It's going to take them a second for every word in the dictionary. So it's just made it extremely difficult for them to attack. So the key with this is you choose an iteration count based on your current execution, your current hardware that you can tolerate for intentionally slowing it down so that you're making it harder for them. Gradually over time, this is meant to get changed. So this is a Crypto 101 talk, but I mean, you need to store and have a thought process about in the future, I might need to make this 125,000 or whatever. I need to migrate my old hashes to these new hash values using 125,000 because every time I change this count, it's going to change what the hash result value is, and it's going to make it take longer if I make it be a bigger number. But be aware if you're talking about password hashing, people are doing all the things we've talked about today in modern systems, but this one is the key to intentionally making it slow. So that's hashing. We've seen how hashing is foundational. It's used for integrity. It's used for authentication. We're about to get into what people normally think about with cryptography, which is for confidentiality. So I want to define the terms we're going to use. So plain text is my original data. Encryption is the process of obscuring that data. The ciphertext is the encrypted data. And decryption is the process to recover the original data. And the cipher is the algorithm I'm using for performing encryption and decryption. And again, I'm using this when I want confidentiality. So again, if you ask the probably average developer and you said, how does encryption work? They're probably going to think about symmetric algorithms. So what happens there is I've got some plain text. I'm going to do encryption using a secret key. I get ciphertext out. When I want to decrypt it, I'm going to use the same key and get back to the original plain text. So that's why it's called symmetric. It uses the same key for encryption and decryption. Primary attack against this, if it's a good algorithm, they just have to brute force the key search. So they just have to start guessing what the key might be and try all the possible keys. Super fast. It's well known. There's good implementations for symmetric algorithms. The problem with them is key distribution is difficult. So if I were to go into the participant list and choose one of you at random and say, I really want to send you a secret during this talk, we kind of have a chicken and egg problem, right? I can't send you using symmetric encryption until I get you a secret key. Well, how do I get you a secret key when I have no way to securely send it to you? So we'll talk about how these work, but that's the primary problem. These are super fast, but the key distribution is a problem. In .NET, symmetric algorithm is the base class. We're going to focus on AES. DES has been broken for a long time. Triple DES is on the border, I would say, if not. AES is by far what most people are using for symmetric algorithms today. In .NET, the symmetric algorithms are block ciphers, which just means they're going to take your message, they're going to break it up into a fixed block size, which we'll choose, and it will encrypt that block. Then it'll go to the next block, encrypt that one. So they're just called a block cipher because they break your message and they encrypt a block at a time. There's padding that we'll talk about. So at the very end, it's unlikely your message is going to exactly fill your block size. So there has to be something placed in the end. There's a couple different choices. I highlighted the choice you want, and I'll show you why you don't want to pick things like zeros. There are a ton of modes for AES. I'm only going to talk about 2, and I'll really show you a third in this talk. You don't want to use ECB. I'll show you why. You want to use CBC or the third one that I'll talk about. When you do symmetric and you do CBC, how CBC works is it says, I'm going to take the first block of data, I'm going to encrypt it. I'm going to take the output of that encryption block as some random input when I do the next block. So we're going to talk throughout the whole talk, randomness in cryptography is what you want. The more random it is, the less predictable your things are. So using CBC is an improvement. ECB just does, I'm going to encrypt the first block, set it aside, encrypt the next block, set it aside. If 2 blocks ever happen to be the same, their ciphertext will be the same. CBC is doing that trick where it takes the first block, encrypts it, and then uses that as some input into the next block's encryption. So when you do that, the question is, well, how do you get random data for your first block? That's what's called this initialization vector. So it's just random data when you're using CBC mode. It's going to help seed the encryption of the very first block. It turns out it does not need to be a secret. So it's not important when I'm finishing and I have ciphertext, I can send you the ciphertext and then I can send you the IV in the clear. The IV doesn't need to be secret the way these algorithms work. However, never reuse an initialization vector. The whole point is for it to be some random data that makes your encryption different. If you reuse it, you're going to get the same result in ciphertext, and people will start to see patterns, which is not a good thing. That's how people break cryptography, when they see patterns. So let's pull up our demo page here. I'm just going to type in test and hit encrypt. So that is my ciphertext. It happens to be base 64 encoded. That's kind of the hallmark of base 64. You'll often see double equals on the end. And then here's my initialization vector. So if you watch when I encrypt, even though it's the same initial plain text, because it gets a different random initialization vector to use every time, the ciphertext turns out different. And that's what we want, right? If I keep sending you the same plain text, I would love it that every time I send it to you, the ciphertext looks completely different. So I'm going to take this ciphertext, this initialization vector, give it to someone else, and then they'll be able to decrypt it back where we started. So let's look at how that code looks. So under symmetric, so I'm using Razor Pages, by the way. I'm not going to focus on the markup and how I get the front end to look how it is. I'm just going to focus on the code. So when you hit encrypt, you're going to come into this method. I created a common method just to create my cipher because both my encryption and decryption are going to need it. So I wanted to have that in one place. So if I go look, we talked before, I'm skipping these suffixes and I'm just using the base AES class. And it lists over here what the defaults are. I want to change it to the better padding so that this is more random padding. So I'm going to switch it from the default. Here's my symmetric key. Again, I don't want to store this here. It's for demos. So that's my key. So then what I need to do to be able to do my encryption, as soon as I create that AES class, it randomly made an initialization vector to use one time. So I wanted to show that on the web page, and it's right now, it's a byte array. So I chose to use base 64. So before I was using hex, I just wanted to show you a different way to take bytes to strings. That's very common. So there is a built-in convert that lets you base 64. That's what I display on the web page. Then to do the actual encryption, I create an encryptor. Again, I need to take my string, convert it into a byte array, and then I do the actual encryption. And then I base 64 the byte array back to a string so I can show it on the page. So again, the thing to notice, AES is well known. It's still considered secure, and it's not much code. Again, without all my comments, it really is not take too much code to use a good, strong, well-trusted symmetric algorithm in .NET. Won't spend a lot of time on this. This is just the reverse. I need the initialization vector, and then I do the reverse, right? I take it from base 64 back to a byte array, and then do the decryption, put it back to the original plain text. So again, that's why you shouldn't write your own. The stuff's available in .NET, works very well. So let's talk about why did I do it with these specific modes. So AES is secure, depending on what mode you use and what padding you use. So let's go change this a little. I'm going to shut off my web server here quick. I'm going to switch from doing the random padding to just pad with zeros. And I'm going to use the ECB mode we talked about before. So ECB is just taking one block at a time and encrypting it and not using the output for anything else. So let me start up my web server again, and we'll show why ECB is not a good choice. So again, just because it's, back to the don't write your own, just because it's available in a framework also doesn't mean that it's the right algorithm or mode to choose. You need to think through why this matters. So if I were to come back here, hit that page again, we'll hit test and encrypt it. So what I want you to notice is every time I encrypt here, the ciphertext is staying the same. It actually is not using the initialization vector because of the ECB mode. So that's the problem, right? Every time this message is the same, I'm going to get identical output. So if you followed it all, World War II, Enigma, how did they break it? They saw patterns in the ciphertext, which eventually caused problems. This is why you don't use that mode. So again, don't use zero padding and don't use ECB. Use the CBC and switch the padding. Okay. So that is symmetric. I will show two more things here that I forgot to mention. One question would be, how do you create keys? So inside the code here, I have a get bytes. If we open this up, I'm in my case with AES, I'm using 256 bits. So I just have that hard coded. I need to use what's called a random, cryptographically strong random number generator. So if you've ever looked at normal math.random sort of stuff in .NET or looked at random numbers in other frameworks, they're usually not very random, right? Computers follow a series of steps, and they're not good about creating truly random things. So whatever framework you're using, you have to make sure that you've got what's called cryptographically strong. So in this case in .NET, this is the best one that we have. So I just use this class and say get bytes. That's how I can actually generate a key. So if I go back to this, I can just call this over and over. Each one of these would be a symmetric key that I could use for AES. So I just wanted to show you that's there. So I talked about randomness, how things aren't truly random. If you're familiar with Cloudflare, which is obviously a big internet provider, they actually have in California, they have a set of lava lamps. So they needed to get truly random data, and they wanted to be able to reach outside of computers and get something that would be non-deterministic. So they have this set of lava lamps in their lobby, and they actually take a picture of the current state of all of these lava lamps, and they use that as part of their random data. So if you go want to read about how that works, it's a good example of for very serious cryptographic things where you need even more randomness. Where could you look for sources of randomness that are outside computing computers themselves? So I just thought that was kind of interesting. Let's talk about asymmetric. So we just talked about symmetric. It's cool. They're really fast. AES is secure if you're using it properly. The issue with it, again, is key distribution, right? How do I get that secret key? How do I secure that secret key? So they came up with what's called asymmetric. So there are two complementary keys, a public key and a private key, which mean what you would expect. If I want to do encryption using asymmetric, I'm going to generate a key pair. The public key I'm going to put on my LinkedIn profile or Twitter or wherever, right? I'm going to advertise that. It's okay for people to see that. It won't help anybody break anything. That's what they're going to use to do encryption to me. So if we look at the picture, I have plain text I want to send to somebody. I will get their public key to do the encryption. As soon as I do that and have ciphertext, I can't even decrypt it anymore. If I don't have the corresponding, so these keys are complementary. If I don't have the corresponding private key, I can't decrypt it, right? Obviously, I just had the plain text, but if this was a day later or whatever, I won't be able to decrypt it. As soon as that encryption occurs, the person has to have the complementary private key. So obviously, my receiver is going to put a lot of effort to make sure their private key is never exposed. And if they do that, they can then take the ciphertext, do the decryption, and get back to the plain text. So this gets around the whole key it makes the key distribution problem less of a problem. If I get the public key from a reputable place and I trust it, and the person keeps their private key secure, this gets around the key distribution problem. So I gave you, for instance, I would feel pretty comfortable with someone's LinkedIn profile if they had a public key, because that's using HTTPS, and unless their account was hacked, I have pretty good trust that's their public key. People do put their public keys in their email signatures. I personally wouldn't trust that, right? Emails are postcards. People can read them, which we don't care about reading the public key, but they could modify them and substitute a different public key. So just think through, how did I get this from a place that I could trust? And again, as somebody publishing it, I'll put it somewhere where they can trust it. Hopefully it hasn't been tampered with. It gets around that key distribution problem. The problem is the asymmetric are like 1,000 times slower than symmetric. So we'll talk about what we have to do about that. In .NET, the base class is asymmetric algorithm. I'm going to focus on RSA for the implementation. So let's go look at what this would look like. Again, I'll just type test. This is what the ciphertext looks like. If I decrypt it, that's the result. So how does this look in code? So again, I have an encrypt. When I hit the button, it comes in here. I'm going to create a cipher. So here I just create the RSA class. I created my public-private key pair. And again, for demos, I pasted it. It turns out I can get an XML representation. This one is both my public and private key for this demo. To do the encryption, I just have to take the plain text string, convert it into a byte array. I just encrypt it. Note the padding that I chose. The PKS CS1 is not considered secure anymore, so please use this for your padding. And then I base 64 the ciphertext. So again, if you look at this, what's impressive about it is its powerful encryption with not a lot of code. This is, again, why don't go try to write your own stuff. This is well known. It's a good algorithm. Take advantage of what you have built in. It's easy to use. So that is asymmetric. Where could I use something like this? So back to my web server. If I had a public-facing web server and I took, say, your credit card, and I wanted to make sure that it was encrypted. So if you think again about goals, I want confidentiality. Sometimes people will say, use hashing. Well, hashing is not going to work because I need to be able to reverse it, right? Sometimes somebody needs your actual credit card number so I can charge you. So I'm going to use encryption. But if I use symmetric encryption, I have a public-facing web server. I would need to store a secret key on my public web server. So I told you before, I treat my public web servers like someone else could own them. So if I put a public key somewhere or a secret key on there somewhere, somebody could compromise it, get my secret key, and then they'd be able to decrypt all my credit cards, which would be extremely unfortunate. If I used asymmetric, I could actually generate a key pair. I'm going to put the public key on the web server. So as soon as I take your credit card and encrypt it with the public key, nobody can decrypt it anymore except whoever has the private key. I'm going to keep that private key inside my firewall, squirreled behind a lot of secure systems, right? If you take the credit card example, I may have one computer that's talking to my credit card processor. That's the only computer that would need the private key. And I'm really going to lock that thing down and make sure it's limited who can get to it, who can sign into it, etc. I've gotten around the whole key storage problem because now this is a public key. If somebody does intercept and break into the web server and get the public key, they can't do anything with it. They can't decrypt anything I've encrypted with it. My risk here is they could replace it, right? If they were to modify the public key and they had the private, they'd be able to use it. So thinking about risks, but from a key storage standpoint, it's a huge improvement. And again, it's hard to take over the web server and change keys and such. So there's a lot of layers there already. Just so you know, it's meant for small amounts of data. So RSA is not able to encrypt a lot of data. First of all, because it's really slow. And second of all, there are algorithm limits of how much it can actually encrypt. But in this example, it would be a credit card number, which is going to be small enough. So if I were to go look at this example, you would come to my public web server, type in your super secret credit card number. I could take that ciphertext now and store it in a database table, do whatever I need to do with it, right? Because as soon as I took the public key and encrypted this, now I've got ciphertext that only the private key can decrypt. Eventually, my internal system would go peel that off and it's going to go talk to a credit card processor. They could do the decryption and voila, get the credit card. Today, a lot of credit card processors do this for you. They'll generate a public and private key specific to your company and give you the public key. The advantage of that arrangement is I will never even have the private key. So as soon as I encrypt a credit card, only my credit card processor can actually decrypt it with the private key. So that's a practical example of where I could use asymmetric. Now we're going to get to digital signatures, and this is really the combination of a lot of things we've talked about so far. So I just want to walk through the diagram first, and I'll show you some code. By default, digital signatures give me integrity and non-repudiation. And so they're going to make sure that whatever I send is not tampered with and that the receiver can prove that it came from me. I'm also going to tack on confidentiality. So that's not by default part of digital signatures, but I'm pretending whatever I'm going to send, I also don't want people to see. So the flow chart here, I've got the plain text. I'm going to encrypt it using public, private, asymmetric like we talked about before. So if I have the receiver's public key, we'll do the encryption and we'll have ciphertext. That's what we just looked at. If I compute the hash of that ciphertext, the key now for digital signatures, I'm going to use my private key and encrypt that hash. That becomes the digital signature. And the reason that works is because the private and public keys are inverses of each other. You'll know my public key, so you'll be able to decrypt using my public key. That will prove that I was the one who signed it. So as long as I've kept my private key secure, I'm the one who signed it. So I'll send you both the ciphertext and the signature. So in the code example I have, I've just got a site here, maybe an e-commerce site. I want to send securely data to another web server via a link. So if I click this, you'll see I'm sending this secret. So again, digital signatures, I don't have to use confidentiality, but I did. And then if I were to go over to the right here, I'm passing both the secret and a signature. And you can see the receiver was able to get back to the credit card number. So let me pull up what that code looks like. So we'll focus on the sender given the time we have here. So I got the receiver's public key. I'd probably really have this stored in a database or something. But again, for a demo, this is their public key that I'm going to use to encrypt it. This is my public-private key. So first I'm going to create a cipher for my stuff that uses my keys. I'm going to use that for signatures. I'm going to use the receiver's public key when I want to do encryption. So here's my super secret. I'm going to convert that into a byte array like you've seen before. I'm going to encrypt it. So this is exactly what we saw before. That was just the asymmetric encryption. So now I have some cipher bytes that I want to send that no one other than the receiver will be able to read. I compute a hash of it. We saw that before. That's just hashing like we've always done. And then now here's the digital signature part. .NET has a specific class where I pass it my sender cipher, which is my private key. I tell it I want to use SHA-512 and it creates a signature for me. Then I just base 64 the secret and the signature, and I end up embedding those onto the URL. And again, if you can appreciate, we've accomplished a ton of stuff here, right? I've just sent you something no one else can read that you can prove has not been tampered with, and you can prove was signed by me. So that's digital signatures in .NET. And again, you can look at the reverse side of that in the receiver code here. The brief part of it is I have keys again. There's a .NET class here called verify signature. So you're recomputing some hashes, pulling the secrets off, but this verify signature will tell you if everything came out okay. So that is digital signatures. I did miss one thing I want to come back to. This is a 101 talk, but I did mention in Symmetric. We looked at AES. There's a new mode for AES. GCM is one of them. What's cool about it is it's true that AES does confidentiality, which is great. But just because it's encrypted doesn't mean people can't tamper with it. I'm going to give you some resources at the end that you can go look at that will explain what that means. So the point with that is just you can have both encryption and you can also have authentication. So it's true that even though something is encrypted and people can't see it, they could potentially still tamper with it. So the code on there is showing you how you can use this other mode to be able to get the best of both. So I would recommend that that's something you use now. Okay, so HTTPS is a good example of combining everything we talked about too, right? So the way HTTPS is, I'm a server provider. I'm going to generate a public-private key pair. I'm going to take the public key and go to a certificate authority like Let's Encrypt. When I go to them, they're going to digitally sign my public key, and that becomes my certificate because browsers know what is called trusted certificate authorities. So they basically know that they trust Let's Encrypt. It's baked into the browsers. So when they come to my website, they're going to get the certificate. They're going to see that it was digitally signed by Let's Encrypt's private key. They can use Let's Encrypt's public key and say, yep, it was definitely signed by Let's Encrypt, so I'll trust it. They'll take my public key out then, okay? So then the browser will say, I don't want to use asymmetric encryption because that would be super slow, right? We already talked about that. So instead of using asymmetric, the browser will create a random symmetric key. It needs to get that secret key to me securely, so it will use my server's public key, encrypt that session symmetric key and give it to me, and I'll be able to decrypt it. Now the browser and the server both have a symmetric key that's fast, and then they do the rest of the encryption. So you can see all the things come together again, where you've got symmetric, asymmetric, digital signatures in a practical place that we all use every day. Okay, I'll be honest with you, key storage is the worst part of cryptography, especially if you think of the world that I'm living in with an e-commerce website. How do I store a secret on a box that I believe can be compromised? There aren't a lot of good answers. I'll refer you elsewhere based on what system you're using. So if you're using Azure, you can look into Azure Key Vault. Depending on what your deployment environment is, they may have mechanisms that add layers on top that allow you to get the best you can to store the key. I personally avoided it when we talked before about credit cards. I avoided the whole issue entirely by not storing a secret on my web server. That's basically how I'm getting around it. By putting the public key on my web server, I don't have that issue, right? The key storage is moved at that point. I won't spend a lot more time on this. Again, it's a 101, but I'll just warn you that that's the worst part, key storage. All right, summary, awesome. So again, don't write your own. I mean, if you take nothing else from this, whatever language you're in, you'll find an AES, you'll find SHA-2 family of hash algorithms. Just make sure you understand what your goal is. I see people confusing hashing and encryption a lot, and they're misusing the wrong stuff. So think first about what is my goal or goals. If I want integrity, I'm going to use hashing. If I want confidentiality, I'm going to use encryption. So just make sure and think through your threats, right? It's important to understand, regardless, all of us have unique systems. You need to sit back like I did for capture the flag and look at it from an attacker's perspective of don't be overconfident, right? Don't think like the Unix creators and think you can't reverse a hash, therefore this is secure. Think through what the threats will be and get your layers of defense. Okay, so I do have a full Pluralsight course, a couple hours that gets into the history and everything if you're interested in that. A good book that I've been using lately is the Python for Practical Cryptography. I don't actually know Python, and it doesn't matter. The book has good Python examples, but it's the best book I've found so far that has very practical advice about the different modes that are not secure and just how you should be using these algorithms correctly. It actually walks through good examples of, why is ECB bad, similar to what I showed, but it explains like, why is MD5 broken? And it talks about how hashing, so it gets another layer. It doesn't get into all the math. If you look at the middle 3 books I have referenced, if you really care about bit shifting and registers and exactly how AES does all of its stuff, look at those books. They'll go into all that detail. I'm not a mathematician and I don't really care about that. I've used all of those books to think about how do I successfully use AES, which those cover. I don't care about the implementation. I'm not writing an implementation of AES. So that practical Python cryptography is very good. The last 2 books I had on that slide were ones that are more history. So one is super thick, the code book, and it's got all the history of, Caesar cipher and all the way up. It goes into Enigma, and it just explains how people have used cryptography and how people have broken it. So if you enjoy the history part of cryptography, which I do, and secret codes, that's where you should go. I think this is the wrap up. So it should have my email, my Twitter, my blog, and a link to the slides and the code.